Good afternoon and welcome to the REYES program, the Remote Experience for Young Engineers and Scientists program known as REYES. My name is Giovanna Gennard. I'm Assistant Vice President for Strategic Communication and Marketing and co-chair of REYES. And I will serve as your host for today's event, Mars Entry, Descent and Landing, Past, Present, and Future. The purpose of the Global REYES program is to offer free virtual learning experiences that increase science literacy, inspire and train future generations of STEM-age students. Our goal is to make science more accessible, diverse, and equitable. Today's discussion with Michelle Munk offers us insight into NASA's successful landing of the Perseverance rover in Jezero crater on the surface of Mars. The most exciting part of the journey is the last 7 minutes of terror, when the rover has to travel through the Mars atmosphere to get safely to the surface. Michelle Munk will provide a behind-the-scenes look at how the system is designed, how entry, descent, and landing at Mars has progressed over the decades, what's special about the Perseverance mission, and what the future of Mars landing might bring. Throughout this webcast, you may submit questions through the Q&A box on your Zoom screen. And following Michelle Munk's lecture, we will answer as many of your questions as time allows. It is now my pleasure to introduce our guest speaker, Michelle Munk. Ms. Munk, would you please turn on your microphone and video so we can see you? Michelle Munk is NASA's Entry, Descent, and Landing Systems Capability Leader and the Principal Technologist for EDL Technologies with NASA's Space Technology Mission Directorate. In these roles, Ms. Munk is responsible for ensuring sustainment of NASA's EDL skills, facilities, and tools, as well as guiding technology maturation. Ms. Munk has experience in orbital mechanics, trajectory simulation, and flight hardware development. She began her career as a cooperative education student and has worked at 3 different NASA centers over her 30-year tenure. Her past work includes the Mars Odyssey Aerobraking Operations Team and Deputy Project Manager for the Mars Science Laboratory Entry, Descent, and Landing Instrumentation, MEDLI suite. She is currently a principal investigator for 2 lunar camera payloads. Ms. Munk holds a BS in Aerospace Engineering from Virginia Tech. She is an AIAA Associate Fellow and has several publications and NASA Achievement Awards, including the Space Flight Awareness Award and the NASA Exceptional Service Medal. Please join me in welcoming Michelle Munk to REYES.
Thank you, Giovanna. Welcome everyone today as we talk about Mars Entry, Descent, and Landing and all the exciting things that are going on in Entry, Descent, and Landing at the current time. It was less than a month ago that Perseverance made that fiery entry into Mars and landed safely in Jezero crater. So we're going to talk about that, what got us there, and what's next in Mars Entry, Descent, and Landing. I have the next slide, please. So what do we mean by entry, descent, and landing, or EDL for short? EDL is really the process of delivering a vehicle from the top of an atmosphere to the surface and, of course, landing it safely. This is what Giovanna referred to as the 7 minutes of terror. When we approach Mars' atmosphere at 13,000 miles an hour and need to get safely to zero at rest, only 125 kilometers vertically later. How do we do that? We have to pass through 3 phases of flight. Those are the hypersonic portion of flight, which we call entry, and that's where the high heating portion and the high pressure are on the vehicle. But we can use that pressure and the aerodynamic shape of our vehicle to guide us to our target. Next, we have the descent phase, which is supersonic flight. And that's really the high Mach number, or the speed of sound, where we're using parachutes or we're turning on engines and getting ready to land safely at our target. And then finally, landing is our subsonic flight. So when we're going less than the speed of sound at Mars, less than Mach 1, we usually extend our landing gear and throttle our engines for touchdown. But we've done this in many different ways over the years, as we'll see in a moment. So finally, EDL is the riskiest part of Mars exploration. And you heard it referred to as the 7 minutes of terror, and it certainly is. But let's find out why. Next slide, please. So why is landing on Mars so hard? First of all, Mars has an atmosphere that's about 1/100th of the density of Earth's atmosphere. We like to say it's too much to ignore and too little to really be useful. It causes our vehicles to heat up, and it means we can use an aerodynamic shape to slow down, but really it's not thick enough to be very effective. Can you click through, please, Raul? Mars is about half the size of Earth, which means it has less gravity, about 3/8 the gravity that we have on Earth. Its mass is about 1/3 as well, and it's far away, so the distance from Earth and the sun makes it quite cold, and it actually also means that signals from Mars, when we're trying to communicate with our spacecraft, take many minutes, anywhere between 8 and 20 minutes, depending on where Mars and Earth are. Mars, yes, are in their orbits. So that's always a factor when we're communicating with our spacecraft. Next slide, please. Oh, and I didn't mention that it's cold there, especially when we're headed out towards Mars, away from the sun. Our heat shield, which we'll talk about in a moment, gets very cold, as well as the rest of our components. So we have to have very good thermal management throughout our vehicle to save energy for the trip. Next slide. So how many times have we landed on Mars anyway? You can see in the red all the failed missions from Earth entities who have tried to land on Mars, and in green, the few that have succeeded. This doesn't even count all of the orbiters that have been sent to Mars that have failed. So you'll see that along this list, only the United States so far has successfully landed on Mars, and that's a terrific achievement. So let's talk a little bit more about how we do that. Next slide, please. So what have our landing missions been? Let's start when I was a little girl in 1976, when the Viking 1 and 2 landers landed. These were the very first landers to successfully go to Mars, and we learned an awful lot about the surface and how to operate there. And actually, the Mars Viking program was managed at Langley Research Center, not far from ODU in Hampton, Virginia. I know we have a global audience today, but I'll give a special shout out to some of the contributions from NASA Langley Research Center for those who are local to ODU. Next, it was a very long time, a 20-year span, until we had another successful landing on Mars with the Pathfinder lander and Little Sojourner rover in 1996. Actually, it launched in 96. And what was significant was that Little Sojourner rover, which was about the size of kind of a cigar box on wheels, was the very first time we had successfully roved on Mars. And you can see how that influenced our landers and our transportation systems of the future. Next, in 2004, we sent the twin rovers Spirit and Opportunity, and they lasted quite a long time. Opportunity was active doing science and roving around the surface until 2018. So it was a very long-lived mission. Next, we had another stationary lander with Phoenix in 2018, 2008. Next, we had the Mars Science Laboratory, which was the first large rover that we'd sent. It and its sister Perseverance are about the size of a Mini Cooper or a golf cart. So just think about that. We went from something the size of a cigar box on wheels to something the size of a small car. So that's quite an achievement. And we'll see a little bit more about how Curiosity and Perseverance landed in a moment. And then a couple years ago in 2018, we had Mars Insight, which is another stationary lander. So you kind of see a pattern. We had landers, rovers, and so we pick our landing sites, and the scientists really drive where we'd like to go on the surface, and that's how we choose our missions. And then, of course, Perseverance that landed just under a month ago on February 18th, that we'll talk much more about. Next slide, please. So let me show you first a short video about how we get to Mars and how Curiosity landed. So again, this was 9 years ago. So we leave Earth and we have our rocket booster that pushes our lander towards Mars. And there's a ring on the back of the lander at this point while it's going out to Mars called the cruise stage. When we get close to Mars, we get rid of that cruise stage and we see the jets on the back of the vehicle that are steering us toward our landing site. Curiosity was actually the first lander to do this. When we get to supersonic flight, we unfurl the parachute, we drop our heat shield, and then our vehicle comes out. Now, Curiosity was the first to land as suspended from a descent stage where there are 8 engines that help us land softly. Once we've landed, those cables are cut, and that descent stage, as you saw, flies away and crashes to keep Curiosity safe. And after that, Curiosity drove away and started doing its science mission. Okay, we can stop that one there, Rahul, and go to the next slide. Now, the interesting thing about Curiosity was everything you just saw was actually a simulation. But we're going to see in a moment how we've improved that with Perseverance. So let's talk for a moment about Perseverance's mission objectives. We are trying to explore a geologically diverse landing site. Up to this point, we've had to land in, albeit exciting, but very flat and non-treacherous terrains to keep our landers safe. But Perseverance has a new technology called terrain relative navigation that helped us get into Jezero Crater, which is quite a different hazardous site. We're looking for signs of ancient habitability. So we're going to an area that is actually, we think, a river delta where water might have once flowed on Mars. And we'll look at a couple pictures of that to talk about it more. We're seeking signs of ancient life, particularly in special rocks. And so in this area where there's a crater and there might have been a lake and flowing water into that lake, we get things that you see on Earth, strata, different layers of rock and sedimentary rock that you see. And the scientists are really interested there because those layers really capture the history of Mars. And that's what the scientists are really interested in seeing. Perhaps most importantly, Perseverance is going to gather rock and soil samples and put them into small tubes so that they can be picked up and retrieved and brought back to Earth by a future mission. Mars sample return has been a goal of the science community for as long as I can remember, decades. And we know that we can't send every scientific instrument that we might want to use all the way to Mars. So it would be much better to bring a rock sample back to Earth so that we can study it in our very extensive laboratories here. And as we've done with moon rocks, we can preserve those samples for the future when laboratory facilities will be even better. And of course, we're trying to demonstrate technology for future robotic and human exploration. And that's something that's very near and dear to my heart because I am really helping guide the technology development for one day sending humans to Mars, which we'll talk about a little later. So you can see how complex Perseverance is, and you can see about the scale of this rover compared to humans. So this is in the clean room at Jet Propulsion Laboratory before it was launched, obviously, and the engineers were working on it and testing it out. You can see it has 6 wheels. It has a very unique suspension system to allow it to drive across the Mars surface. Up here in the top left, there's mast cam, so it's on a long boom that can extend upward so it can see farther over the horizon and help decide where to drive Perseverance. So next slide, please. So this is our landing site. This is quite an interesting landing site. Look at the river formations around here. This almost looks a lot like our Mississippi Delta as the Mississippi River flows into the Gulf of Mexico here on Earth. So the scientists are very excited to see what sediments and rocks are here. In particular, there are clays and carbonates. So if you're interested in geology at all, this is going to be a fantastic mission. Next slide, please. So what's new about Perseverance entry, descent, and landing in particular? Well, I've talked a little bit about the landing site. On this figure on the left, you can see kind of the outline of what the Mars Pathfinder landing ellipse, the area where we might land, look like. It was about 125 miles by 45 miles, or 200 by 70 kilometers. So if you're uncertain about where you're going to land in that large area, you better put that in a really big flat place, which we did. Then, and to compare to that, Phoenix and InSight had landing ellipses about 130 by 27 kilometers. So we've done better over time just by knowing better where Mars is in its orbit and having better navigation technology for knowing where our lander is when it gets to the top of the atmosphere. Curiosity, you see the circle here, had an even smaller footprint of about 25 by 20 kilometers. And of course, it landed safely as well. But Perseverance had even a smaller landing site, as you see here. And that's due to new technology in deploying our parachute based on where we are relative to the landing site, instead of deploying it based on the speed that we're going. Now, knowing where we are versus our landing site is enabled by a new technology called terrain relative navigation. We have a camera on board that's taking pictures of the surface as we approach our site. And it's comparing those pictures to an onboard stored map that was taken from pictures of from the Mars Reconnaissance Orbiter. So by comparing the pictures of the ground to the picture that's stored on the rover, we can pick out landmarks and then know exactly where we are compared to the surface. And that's what allowed Perseverance to have such a small landing site and allowed us to land in this very hazardous region. You can see this mountain range here and this cliff and large craters in the area. We would have never been able to land in such a hazardous place before without terrain relative navigation. So this is a huge step forward in precision landing and safe landing that we'll use on the moon and on Mars. So what else do we have that's new? We have lots of cameras that are operating during entry, descent, and landing. So remember, during the Curiosity video, I told you that that was all simulation. Well, now we're going to see actual pictures coming back and video coming back from the actual entry, descent, and landing. And I'll show you that in a second. But we engineers have been wanting EDL cameras for a very long time. We had 3 cameras looking up as the parachute deployed, which is really exciting. We had descent stage downlook cameras, and so we're looking down from where those engines are as the rover is lowered. And then we have rover upload cameras actually looking up at the engines as well. And then we have download cameras looking at the surface in addition to our terrain relative navigation camera. And then, of course, all of this, the rover and the descent stage, are folded up inside the heat shield, which protects us during entry and descent, and the back shell, which covers the rover and also protects it. So let's go to the next slide. Okay, so here's the video that you might have seen on February 18th, but it really never gets old. So here we go. We're already in the atmosphere at this point, so it's a little later than the other video I showed you. This is the control room out at NASA's Jet Propulsion Laboratory. And there we get to see our parachute deploy. What a fantastic sight. Now, engineers can use these videos to compare to what they predicted would happen, and we can improve the parachute on future flights. And there goes the heat shield. Remember, it has to drop off so that we can see the surface.
And the heat shield has been separated. This allows both the radar and the cameras to get their
I'm not sure if you can hear. We put the video on pretty low so that I could talk over it. And if you're following along on the bottom of the video, there's a little icon that tells you kind of where we are in the timeline and what's happening. So here you saw the heat shield separated. I'll talk more about the heat shield in a moment because NASA Langley had a really significant part in some things you could see on the heat shield. So now we're coming in and we're using our terrain relative navigation.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers.
And look how big that cliff is that we're heading right towards, but we're going to miss it, of course. And there's a big crater down there, so we have to miss all of those hazards. So we're using our terrain relative navigation camera. This is actual video from the surface of Mars, which is incredible. So now we're getting closer. We're still on the parachute. And in a moment, we're going to let the parachute go and turn our engines on.
That the lander vision system has produced a valid solution and part of terrain relative navigation.
So that was our lock where our map that we saw in front of us matched the map on board. And so now we know exactly where we're going. And if we were seeing a hazardous crater or something in our landing spot, we're going to divert. We have a little bit of propellant and we can move our lander over away from a hazard.
Velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
So we've gotten rid of the parachute and the back shell now.
We have completed our terrain relative navigation. Current speed
Here we go.
30 meters per second, altitude of about 300 meters off the surface of Mars.
So we're about 3 football fields up from the surface. Now the engines are on, and look at what the engines are doing to the surface. They're kicking up a whole lot of dirt. There goes the rover, and then there's the rover looking up at the descent stage. And you can see that you don't see an engine plume. That's because of the type of fuel that we're using. But it's really thrusting.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So I could watch that all day. I don't know about you. So let's go on. And here is the first image that was sent back from the Perseverance rover. And you can see that there's a few rocks around, but it's a pretty nice flat area, which is what we wanted from the terrain relative navigation. This one is just a black and white picture, and it has a dust cover still on the camera, so it's a little less sharp than some of the other images that you might have seen more recently. Next slide. So where is Perseverance going to go? This white dot over here is our landing site, and we are going to rove through these really interesting areas. You can see flat places where it looked like water might have been standing, and then we're going to perhaps go up over the hills and into this more treacherous area to try to get some really interesting samples of that stratified rock. So we look forward to a really long mission from Perseverance. It's really only supposed to last 1 Mars year, but we hope for a lot more because most of our rovers and landers last a lot longer than we anticipate. Next slide. I talked to you a little bit about the heat shield, but you know, we as engineers, we love the sight of the rover safely on the surface, but we really want to know how we did. How did we design the EDL system? Was it an A+ design, or was it a C- and we almost failed? So that's what we really wanted to know. We put some instruments, and actually NASA Langley led this effort. We managed it and developed a lot of the instruments right here in Hampton, Virginia. It's called MEDLEY, the Mars Entry, Descent, and Landing Instrumentation 2, because we did this on Curiosity as well. So we put thermal plugs so that we can sense the heat as it goes through the thermal protection system on the heat shield. And we also sense the pressure of the Mars atmosphere as we're flying through it. This will help us design vehicles better in the future. On the back shell, for the very first time, we were able to put some instruments as well. We had one pressure transducer and several thermal plugs to understand the temperatures. We also had a direct sense of the heat through a heat flux sensor, and we had a radiometer, because as the hot plasma comes around the edge of the heat shield, it tends to radiate or send radiant heat towards the back shell. That's a significant heating phenomenon that we've actually only discovered and understood better in the last few years. And so we definitely wanted to take this chance to make a direct measurement. We also designed and built the electronics that take the signals from all of these sensors and send them to the rover. We built that right here in Hampton. And so we got a little bit of data on the way during EDL, but we had to wait for the bulk of our data to come back once the rover was safely on the surface and it could send that signal, all those data back to Earth. We're very pleased to report that we got all of our data back on about 3.5 days after Perseverance landed safely. So we're using it right now to see how we can make the next landers even better. Next slide, please. So how do we get from, the rover that was sitting in the laboratory to the surface of Mars? How do we actually design the entry, descent, and landing? Well, it's quite complex, as you might imagine. But one of the key things is that we can't really test it from start to finish on Earth. That's because Mars' atmosphere is so thin compared to Earth's that we would have to take this vehicle up to 100,000 feet altitude to get a similar density. And even then, the gravity would be wrong. So we can't really test the system all the way. The way we do it is actually by testing it in a computer. So we use all the models of all the different aspects of the vehicle. And really, it's just one big physics simulation. Think Newton's second law, F equals ma. So we put all the m's, all the masses in there. We put all the forces in, and then we get the acceleration of the vehicle and how it flies. We actually do this at NASA Langley to help the JPL team on every Mars mission. So we have people at Langley who are an adjunct to that JPL team running trajectories all day long, even to the moment of landing. So it's really exciting time. Unfortunately, our team couldn't be together with the JPL team this year due to COVID, but we had a few people in the control room here at Langley, as well as the Medley team in a separate control room. So let me tell you a little bit about these models. So we look at the aerodynamic shape of the vehicle and how it's going to fly through the atmosphere. We test that at wind tunnels at Langley and other places in the country. We build those models through computational fluid dynamics, and that's one input into the entry, descent, and landing simulation. We want to know where the mass is in the vehicle to a very detailed level, which also tells us how it flies. We work with the people who are guiding it on the way to Mars to understand where it is relative to the Mars atmosphere, and we put all that into the simulation. We put models of the terrain and the gravity into the simulation. We model the parachute, and that's based on wind tunnel data as well as flight tests. We model the engines of the descent stage. the inertial measurement unit, which tells us the accelerations on the vehicle, the radar that senses the ground and tells us our altitude when we get close, and also those little jets that you saw in the back of the vehicle that were firing to steer us through the atmosphere, as well as model of the flight software. We actually put the flight software into our simulation. Then we put all this together in a statistical model called a Monte Carlo simulation. And that means that we don't know everything perfectly. We don't know what the winds are going to be at Mars the day we get there. We don't actually know what the density of the atmosphere is going to be at every point that we're flying through. And so we model those uncertainties as statistical distributions. We combine all of them together and we run the simulation literally millions of times. And that's what gives us confidence that in the worst case, no matter what we could think of that would happen, the vehicle will be safe. If we run the simulation and we find failures, the engineers at JPL and other places around the country work together to try to cut out that risk or mitigate that risk so that we have a higher probability of a safe landing. So that's how the engineering model comes together and actually helps certify the vehicle and tell us that it's safe to land it. Next slide, please. So what's the next step? I mentioned that Perseverance is going to pick up samples for later return to Earth. So this is what that mission is going to look like. It's going to have many different components, many separate vehicles. First, we're going to start at Earth, of course. We're going to launch and go out to Mars. This looks very similar to what you just saw. We're going to land, and we're going to have a stationary lander that has a rocket on it. The samples are going to be retrieved by a rover that is contributed by our partners in the European Space Agency. They're going to pick up those sample tubes that Perseverance has left behind, put them into the rocket. The rocket will then launch by itself from the surface of Mars and the lander. It will go up and send this little ball, which is where the Mars samples are. They will be put into an Earth capsule that's on an orbiter that's also supplied by the European Space Agency. That orbiter will bring the samples in the capsule back to Earth, and the capsule will separate a few days out and bring those samples back to Earth and land in Utah. So that's the plan. Here's one graphical representation. You see the ramp that the rover can drive up to put the samples in, and now we have the rocket blasting off. And here is a view of a prototype Earth entry vehicle, the little capsule that the samples are in the Utah desert. This capsule is actually being developed and delivered by NASA Langley and our partners NASA Ames Research Center out in California. Together, we're designing this vehicle to bring those Mars samples back. So we're really excited about that role on this mission. Next slide. So what about after Mars sample return? What about sending humans to Mars? Well, we've talked about the ways that we've done EDL in the past, and really, if you look across this table, it shows you to scale all of the Mars landers and what their aeroshell shapes look like. And you see that they're all pretty similar. They've all used supersonic parachutes. All of that heritage comes from our very first landers back in 1976. So we've really just kind of changed things a little bit here and there to land now our Mini Cooper on the surface. But to take humans to Mars, we're going to have to land not a Mini Cooper, but something more like a 2-story house. Humans need a lot of stuff. They need a lot of volume, they need food, they need air and water, and lots of science equipment too. And so we think that we're going to need an aeroshell about 16 meters in diameter as compared to the about 4.5 meters we've sent so far. We also know that supersonic parachutes are not going to be effective for a vehicle this big. And so we're going to have to use our engines, just turn them on while we're still in descent at supersonic speeds. Those engines are what's going to help us land safely. And then we'll keep them on until our very precise soft touchdown. So it's really going to take a new way of thinking about entry, descent, and landing to land this big vehicle that's maybe 16 or 18 meters in diameter and weighs 50 tons to get about a 20-ton payload for the humans to live in. And we're going to have to do this a few times, land these things all close together so that the humans have their ascent vehicle to return to Earth, close to their habitat and close to their laboratory. So next slide. So I mentioned a 16-meter heat shield. Why haven't we done that before? Well, here you see a picture on the left of the Mars Science Laboratory inside its launch vehicle, and we call this the shroud, the part that covers the vehicle on launch. You can see that the maximum diameter of this heat shield, 4.5 meters, just barely fits inside the launch vehicle. Well, remember when I told you that the density of Mars' atmosphere was about 1/100th of Earth's? Well, that means that we need a large surface area to slow down even bigger, heavier payloads. Well, we can't fit those in a launch vehicle. Here would be the Mars Science Laboratory in a launch vehicle, and we need something much, much bigger, but it won't fit. Engineers at NASA Langley actually invented the idea of an inflatable heat shield, and we're going to talk about that a little bit more. We're designing those and building those right now so that they will be ready to take humans to Mars. So you can see here in this picture, if we had the Mars Science Laboratory trying to fit in a launch vehicle, we could only take a little bit over 3 metric tons with our 4.5 meter heat shield. If we wanted to take something up that would bring back 3.5 tons at Earth, we could use an 8.5 meter heat shield, and we could stow it inside the launch vehicle and open it up when it was ready to come back. Next slide. So here's how we would scale up our inflatable heat shield. We've actually tested this technology twice at the 3 meter scale from sounding rockets from Wallops flight facility on the eastern shore of Virginia. The latest one was in 2012, just a couple weeks after Curiosity landed. Both of those tests were really successful, and they showed us that the inflatable heat shield is a very good concept. We are currently building a 6 meter article that will be flight tested next year. It will come in from low Earth orbit and give us Mars relevant heating and pressures so that we can see how our big heat shield behaves. This will be the largest heat shield that's ever entered an atmosphere. If we wanted to bring mass back from the space station, say a big module that we wanted to refurbish or learn things about, we could bring it down with an 8 to 10 meter article. Many companies that are building rockets are also interested in reusing those rockets and not throwing everything away, as you see from SpaceX, for instance, where they bring their booster back and land it on a barge and reuse it again. Other companies want to do the same thing, but they want to bring back the engines or the stages in a different way by using an inflatable heat shield to come back safely through the Earth's atmosphere. So we are planning with companies to demonstrate that at 12 meter scale. And so you see that this progression makes us in a very good position to make an 18 meter heat shield for a human Mars entry. Next slide. This is a little graphic of the flight test that we're planning. It's called LOFTED, the Low Earth Orbit Flight Test of an Inflatable Decelerator. And it will fly next year in 2022. It will go up on as a secondary payload and inflate outside the Earth's atmosphere, come back in and eject its data that it captures from its entry, comes down on a parachute and hits the water, and will send a ship out towards the recovery area to pick up a data recorder that's floating nearby. Next slide. So you've seen a little bit about how we have been to Mars in the past, how we're going today, and we've talked a little bit about the technologies that we'll need for sending humans and larger payloads in the future. I hope this was informative, and I look forward to your questions. Thank you.
Thank you, Ms. Munk, for talking with us about the shortest and most important part of Mars exploration. That's entry, descent, and landing, and as you've been referring to it in short, EDL. Now we will take questions from our live audience. And to our audience, a reminder that you may continue to submit your questions into the Q&A box on your Zoom screen, and we will answer as many as time allows. So for our first question today, how long have you worked on this specific project, and what has been the most satisfying part of your job?
Well, let's see. As my bio said, I've been working in entry, descent, and landing for about 20 years now. I've had different things I've been doing. My most exciting and most rewarding was working on the heat shield instrumentation for the Mars Science Laboratory Curiosity. So I did that from 2007 through landing in 2012, and even afterwards, we made sure that we analyzed all the data we got back very carefully, and we published all of it, and we applied that knowledge to future missions. And so seeing your hardware, knowing that you worked on it for so many years and sent it to another planet, and in the Curiosity video, that shot of the heat shield flying away, you could see our hardware on the inside of the heat shield. So that's a bittersweet moment, because your hardware has done its job, but now it's trash on Mars. So it's a very exciting thing to be part of a large team that really gets to accomplish something like that.
And knowing that only about half of the missions that are ever sent to Mars by any space agency have been successful, and that hundreds of things have to go just right during this nail-biting drop, and that Perseverance was able to handle everything by itself. Tell us what it is like for someone like you to witness what you described as the 7 minutes of terror.
Well, I hope I didn't get too teary when I saw the video, because I do every time. It's just, once I know the people who were in that room, many of them, and I know how much sacrifice everybody gives. It's time away from your family, it's long hours, but it's the most rewarding thing to interact with, other people around the country and really around the world to do something so challenging. And it's, you're nervous when it's going to happen, because you're like, oh gosh, have we forgotten anything? So, there's always that slight chance that, something has happened. But, it's awesome to see it all come together and to be successful. And it really shows us that working together across all types of boundaries, even in this COVID environment, was especially challenging, but it's so rewarding, and it really gets at, our most fundamental needs are to, do good work and to, be with other people and be creative and succeed at things together.
And so even though it sounds like it was a little bit terrifying that day, it sounds like there was still a lot of fun to be had in that moment, and also even in preparing for it. One of them that I read on the news is that there was a secret message that was encoded into the underside of the parachute. Can you tell us a little bit more about that?
Yes, our friends at JPL sneaked that in. So outside one of the buildings on site at Jet Propulsion Laboratory, there's a slogan that says, "Dare mighty things." And one of our engineers, actually, who worked at NASA Langley for quite a while and then went to JPL, actually made a code in the parachute underneath that the parachute cameras would be able to see, and it was the coordinates of that message. So I think, dare mighty things is definitely fitting for an exploration mission of this type.
It sure sounds like that. And I was curious to see when you talked about all the people that that worked on this project, about how many people total worked on the project?
I'm not sure of the total numbers, but it's certainly hundreds. So, you know, JPL leads the mission and builds a lot of the components there at Jet Propulsion Laboratory. As I said, NASA Langley contributes to the trajectory and the certification of the vehicle, and also that instrumentation. We work on the aerodynamics and aerothermodynamics and testing. And if you think about all the people at all the test facilities and just, you know, people who help us write contracts to buy hardware and, you know, all kinds of different jobs that contribute to the overall mission, it's just kind of mind-blowing. And of course, our vehicle is, our aeroshell in particular, is built in Denver at Lockheed Martin. And so we have a large space company who helps us build the vehicles and get them down to Kennedy Space Center. So then you think about all the people who work on launches and you know, everything that has to go perfectly there as well. So you know, it's not just Perseverance, the rover, it's the aeroshell around it and the system, and it's, you know, the rocket that we put it on, how we move it around the country. So for sure, hundreds, if not thousands of people worked on this since pretty much the day Curiosity landed. We've been working on this mission.
So rewarding. And I was really curious, knowing that the pandemic happened, how did this mission help NASA innovate the way that you collaborate to bring this mission to fruition despite the pandemic, when you're working with these different teams in different locations?
Well, we definitely had to step up our collaboration efforts. You know, we're a pretty collaborative agency anyway, but it's a lot harder sometimes to you know, do some of the detailed work that needs to be done without being face to face. So you know, I kind of say for me it's been a double-edged sword, because I haven't had to travel, I haven't been able to travel, but on the other hand, you know, interacting face to face and, you know, creating relationships and just sharing life with your coworkers, not being able to do that is really hard. So, you know, we have always, like I said, been very collaborative, but we've started using new software to, you know, do meetings. I will say we have a lot more meetings online. And working across time zones is always a challenge, but and we, you know, we have to move large amounts of data back and forth across the country anyway. But you know, to have the Medley support room and the trajectory support room at Langley, without anybody out at JPL for us this time, we really tested those connections quite, you know, a lot to make sure that they were in place, because it was a lot more critical this time than it has been.
And when I think about earlier how you said the amount of time that you've been putting into this project, and then you multiply it by those hundreds or thousands of people that were part of the project, I also think of the trailblazing work of others, including ODU's very own Professor Emeritus Bob Ash and some of his students. They decades ago pioneered the difficult task of showing the benefits of long duration, deep space and interplanetary surface exploration. And they also worked on that MOXIE in hopes of being able to create the oxygen. And so I was wondering how their work and your work continues to build on over the decades. For our young audience members, can you tell us how long it may take for some of the work that you are working on today to be seen in future missions?
Well, you know, you get small bits of it. So like I said, terrain relative navigation, we've been wanting for so long, and we finally got it. And it's going to be the foundation. So we're going to see terrain relative navigation on missions to the moon as early as later this year. So it's not just Mars, but other planetary missions as well that bits and pieces feed forward to. MOXIE, in situ resource utilization, I think is just critical for our long-term habitation. And we're, learning lessons from all the work over the years on ISRU for Mars and how that can help us on the moon. So I didn't really have time today to talk about NASA's Artemis program, but we are planning to put the first woman and the next man back on the moon at the South Pole by 2024. And so there's a huge amount of work going on right now to enable that. And part of that is being able to live on a planetary surface. And so we'll see some of these things come to fruition very, very quickly. Just not at Mars yet, but at the moon. And so we can learn so much from going to the moon and having a sustainable presence there. It will teach us things about logistics and repairs and, like you said, living off the land, in situ resource utilization. We think we're not going to have to just, find water ice to make oxygen and, get water for the crew, but perhaps we'll be building shelters out of regolith to protect the astronauts from radiation. So all that work is going on, and it's going on primarily in NASA's Space Technology Mission Directorate. So we're investing in technologies to go, like propulsion systems to move us around more quickly and more efficiently in space, land, which is really my area, living on the surface, and then exploring. How do we access permanently shadowed regions on the moon to find that water ice? And how do we, have autonomous vehicles to help the humans? And so there's a whole host of other technologies that we need to develop, but we could see them in use very rapidly as early as, after the first missions in 24. We'll be trying to improve our sustainability and build up those bases by 2028.
And we're really hoping that some of the people attending today's session may be the future scientists and engineers that will help us build that technology.
Absolutely.
One of the questions we had was, will EDL at LARC, which is the Langley Research Center, work on missions to the moon and other celestial bodies like Titan on the Dragonfly mission, or is it its focus on Martian EDL?
Great question, and thank you for that. No, Langley does all things EDL. We support we have supported the Orion capsule development, as well as commercial crew, as we see private companies taking humans up to the space station and returning them. And we are also very involved in all the planetary entry, descent, and landing missions. We are the lead for the deorbit descent and landing phase of the human landing system. So that's the first set of landers, human landers to the moon, as well as Dragonfly. We are partnered on proposals for new missions such as Venus, and in the future, hopefully Uranus and Neptune, as well as Saturn, will be on the horizon, because the scientists have lofty goals of going to the outer solar system and learning more about those bodies as well.
And somebody was asking, what would happen if a planet encircling dust event had been happening when Perseverance arrived at Mars, which is one of the things that your team has to prepare for? Was that part of the Monte Carlo simulation?
That's a great question. That was not part of the Monte Carlo this time, although we do kind of envelope the full range of densities that we expect to see. We have quite a bit of data, from years and years of orbital missions at Mars. And so that helps us narrow down the periods in Mars year when it's more likely for us to see one of those planet encircling dust storms. Those usually occur in the southern hemisphere summer. And so we, when JPL and we're first designing the missions, we try to avoid those times of the year if at all possible. We have so far, although InSight got pretty close to that time of the year. And so we've got a few different effects to account for there. One is possible erosion of the heat shield material by the dust while we're flying through it. And we actually did some testing on that to look at those erosion effects. And we're continuing to do testing and improve our models for future missions in case we need to do that again. And then the other parts are the increased density that comes from dust storms, because the dust particles absorb heat and make everything, they call it blooming. The atmosphere gets a little thicker and a little bigger. And we put that all into our models if it's that time of the year.
And speaking of the models and simulations that you work on, an audience member would like to know about how long do those simulations take, and when do you know that a simulation is to your satisfaction?
That's a good question. You know, individually, they don't take very long, you know, a few minutes. We do have, you know, clusters of computer processors that we use, so we don't normally run large cases on our desktops, but our laptops, but we do use CPUs for these computations, and we usually run about 8,000 cases at a time. And when it's to our satisfaction, you know, we do testing along the way as we build up the simulation. Before we put 8,000 cases into the computer, we'll do a couple check for convergence, make sure all the numerics are behaving the way we think. And then we test our models. So, you know, we start with our basic simulation, and every time we update a model, we have a series of test cases that we run to make sure that, you know, incorporating that model hasn't messed up anything else in the simulation. So very rigorous testing and configuration control and documentation all along the way. But so an 8,000 run case could take, you know, overnight-ish to a couple days, depending on, you know, what models we have in there. I'll also mention that we start building up the simulation very early in the mission development. So this simulation has existed since about 2013. But now it has a whole lot more fidelity. So we build the simulation as the vehicle gets built. And so it gets more and more complex, and it runs a little more slowly.
It's fascinating to me how you use simulations to find out what is the best landing spot, right? But then as the rover is descending, there is a point where it has to descend autonomously, right? Did I read that right? And so I can imagine, you know, you prepare and you simulate, but there comes a time when it's going to be on its own for a little while, right? And you almost like have to probably cross your fingers and make sure that all the math and everything that you did was correct. So can you tell me more about the role that autonomy plays in this mission, and then also in future missions?
Sure. The whole EDL is actually autonomous. So it actually has happened by the time we know that it has happened, because of the signal time to get back to Earth. So when Perseverance landed, I believe the lag was about 11 minutes. So Perseverance had been sitting on the surface for 11 minutes and we are powerless. And so that's the thing that really makes it the 7 minutes of terror. So the last time, of course, we're listening to the vehicle and it's sending us, you know, I'm okay and I'm doing this and this happened. So there are some small software commands that can be sent before EDL, but really, you know, nothing we can do because it's all happened already. So autonomy is huge. That's why we do so much testing in the simulations, just to make sure that, you know, every little fault that we can think of, we've accounted for and tried to think of a backup. In the future, you know, it remains to be seen how we will use autonomy, especially when we have humans on board. But, you know, the thought has always been that if you have a crew, we call them a deconditioned crew. They've been in 0G for, you know, 6 months or more, probably. unless we get some really advanced propulsion systems, which we are working on. But, you know, a nominal 6-month trip, even if you exercise for 2 hours every day to try to keep your muscles, you know, fit, you're not going to, your reaction times may be slower than you might think. So the landings will be largely autonomous. And this is a conversation that's happening right now, of course, for lunar landings. You know, how will our lunar landings of today look different than those that the Apollo astronauts did? So all of that is very much being decided right now.
And tell us a little bit about what future missions to Mars may look like. For example, what would a day be like when humans are able to explore Mars?
Well, I think it's going to be so exciting. You know, we're going to have pressurized rovers to drive around on the surface. We're going to have, you know, excursions to go look at interesting formations and collect samples. And of course, we'll have, you know, time analyzing samples inside and doing science, monitoring the weather, and then monitoring systems, doing experiments. So, you know, we talked about MOXIE a little bit earlier. You know, there's going to be a lot of things happening to keep our vehicles and the habitats and everything running. And so I'm sure there'll be a lot of diagnostics and things to do to make sure that the astronauts are going to stay safe and efficient. But, you know, like on the space station, I think we'll have a nice mix over the day of maybe doing an outside excursion, doing some indoor science, having some exercise time, and, you know, having time for relaxation and camaraderie with your crewmates.
What advice do you have for anyone who's considering working at NASA one day, especially young women who may want to follow on your steps? So it's not just working on Earth, but perhaps somebody who may also want to travel and explore space.
Yep, absolutely. You know, there's always, not always an open call, but there are many open calls for astronaut crews. And so be on the lookout for those. I would just say if something interests you, you know, we've talked about a whole host of things today, you know, science, geology, there's going to be lots of biology and medical things. You know, food preservation is, you know, a big area. What's our food going to be like? Is it going to be nutritious after we haul it through space for 6 months and want to eat it, you know, after 2 years on the surface? So just, you know, engineering, science, biology, all the things that you could think of in STEM probably could relate somehow to our future exploration missions. And so, you know, if you have an interest at all, I would encourage you to read and get good grades in science and math, of course, but look for opportunities to engage. We have lots of opportunities for college students to help on NASA missions or do small projects. I would also, you know, highly encourage that you do an internship at a NASA center, because that's the only way you really get a good feel for what we do every day and whether you're going to like it or not. The most important thing at the end of the day is that you like your job, the thing you're going to be doing, you know, all day, every day. So I'd say if you have a passion, you know, go for it. Don't be shy, study hard, work hard, and make those connections. And chances are you can work wherever you want and do whatever you want.
And I know we're just slightly over time, but I do want to ask you one last question, and that is, what inspired you to pursue a career in science?
I really, I grew up watching the space shuttle launch and land, and I really loved airplanes, but I was really intrigued by space. And when I got to, well, what really inspired me was that I had a relative who went to Virginia Tech and co-opted and worked at Wallops. And so I knew that if I went to Virginia Tech and co-opted, I could get a job at NASA. So that's what I did. You know, you got to consider that I grew up without internet, so I had to rely on, you know, what teachers told me or what I read, or, you know, what I knew about anecdotally as, you know, my only connection. So it all worked out, and I was a cooperative education student, and I started at Johnson Space Center in Houston when I was 19. So just haven't looked back. It's always been exciting ever since.
That's really wonderful. Thank you for sharing your story. And for those of you that are still watching and are still here with us, I do want to encourage you to get involved with a Virginia Space Grant Consortium locally here in Virginia. Also, we know we have some people from Puerto Rico, but most states have a Space Grant Consortium, and they do give wonderful opportunities to work at NASA and other areas, as well as check with your local university like ODU. Like you said, we do have some cooperative programs where students get hands-on learning experiences at NASA Langley, NASA Wallops, Jefferson Lab, and others around the area. So we really thank you for being with us today and sharing your journey, along with the work on EDL that you have done. And we look forward to following your work and its impact on the future of space exploration. And for further science inspiration, I encourage your audience to sign up for the ODU REYES virtual summer program. Registration is free, and it's now live at odu.edu/REYES. And on March 30th at 3 p.m., we will be exploring the laws of nature and its implication for a simulated universe. So today's session has been recorded, and if you'd like to watch it again or share it with friends, you can access it from the REYES website at odu.edu/REYES. On behalf of Old Dominion University and the REYES program team, I would like to thank you, Michelle Munk, one more time for joining us today. To our audience, thank you for tuning in, and this concludes today's program. Please have a wonderful rest of your day.
Thank you for having me.
Thank you for being here.